easy. The last question is little bit conceptual. So this is the question. Diameter of spherical conductor is given as 1 meter. For the spherical conductor, capacitance is given by 4 pi epsilon naught r, and diameter is given as 1 meter. So radius is equal to diameter by 2. That will become 0.5 meter. And when you will put the value, this 4 pi epsilon naught, we have 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power 9. And when you will inverse it, then it will become 1 upon 9 into 10 to the power 9 and into radius 0.5. Then you will get the answer. I have just already calculated the answer. This is 5.55 into 10 to the power minus 11. 11 farad. The unit of capacity is farad. Okay. Hello Nawal, how are you? Okay. We are just discussing the question question of the test, and you have not sent me the solution. Please send me the solution. And after this, we have this question. This is very simple question. Calculate the capacitance of parallel plate condenser of two plates. Area is given, separated by distance, and this is the parallel plate capacitor, and a glass sheet is filled here of dielectric constant K is equal to 4, and we have the formula K epsilon naught A divided by D. Put the value of K epsilon naught 8.85 into 10 to the power minus 12. Area is 100 into 100. 100 into 100 become 10 to the power minus 4. No, sorry, 10 to the power 4. 10 to the power 4. And when you will convert this into
be 1 meter square.
Yeah, 10 to the power minus 4. This will become. And divided by the distance, this is in mm. Then you will multiply it 10 to the power minus 3. And after the calculation, I have already calculated, you will get 17.7 into 10 to the power minus 9 farad answer. This is the very easy question. This question is very easy. Question number 3rd. So see here is a capacitor charged from 50 DC supply. Capacitor is there, and this capacitor is connected with some supply DC supply of 50 volts. This capacitor have some capacitance also, and the charge across this capacitor is given Q. Charge is given 10 micro coulomb. Charge is equal to capacitance into potential difference. Capacitance is equal to charge divided by potential difference. Charge is micro coulomb 10 to the power minus 6 divided by this will become this 50, and answer will come out to be when you will calculate 0. Yeah, you are right. 0.2 microfarad, and you can write in the farad also, no problem. And we have to find the energy also. So we have 3 formulas. We have 3 formulas. You can use any of the formula. You can use any of the formula. We have energy stored in the capacitor due to this battery. This battery is the charge to the capacitor, and capacitor will charge, means this battery is providing the energy to the capacitor, and this energy is given by the half Q square by C, and also half CV square, and also half QV. You can use any of the formula, you will get the answer. I am just using half QV. Q is given as 10 into 10 to the power minus 6 micro coulomb, and potential is 50. You will calculate, you will get 250 into 10 to the power minus 6 this will become 25, and 25 10 the 250 into 10 to the minus 6, and unit of energy is joule. This is energy stored. And the last question is a good question, I will say. Matthew, you have just one step away from the solution. You have just
Oh,
calculated
okay,
the
sir. Yeah. Even at the end of the
value.
paper, I felt like it was a bit incomplete.
Yeah. You have just calculated the whole part, but just in the last part, you have just not put the value of Q1 and Q2. That is fine. I am solving now. See here. See the concept. See the concept. Two charged spheres conductors of radii R1 and R2, spherical conductor they are. Suppose one conductor is this and another conductor is this, and they are having the radius R1 and radius R2, and they are saying two charged conductor. Charged means initially also they have the charge. Initially also they have charge. And after that they are saying that when connecting wire, now you have connected these two spherical conductors with a wire. Now leave this question and just give a minute here. Heat flows from higher temperature to lower temperature. Heat heat flows from higher temperature to lower temperature. In the same way, charge flows from higher potential to lower potential. And for the analogy, I am telling this question from the analogy. If you have a water, uh, if you have a container of water, uh, here you have water in container 1, here you have water in container 2, and the temperature of this water is T1 and temperature of this water is T2. Means suppose this is hot water, this is cold water, and you have experienced this already. When you mix two waters, what will happen? What will happen? Heat will flow. Heat will flow until the temperature of both the hot water and cold water will become same. This is the phenomena will happen. Heat will flow in case of water. When you take the hot water and mix in it a cold water, and after a certain period of time, what will happen? The temperature of the mixture will become same. In the same way, this have some charge, this have some charge. I am just supposing this have Q1 charge initially, this has Q2 charge initially. We don't know initially what is the charge, so I am just supposing. And finally, what happened? We have just connected this system with a connecting wire. This is the connecting wire. So connecting the wire means this time the charge will flow until the potential of both the conductor will become same. On connecting the wire, charge will flow, and if you can suppose Q1 has greater charge than Q2, So charge will flow from, this is sphere 1, this is sphere 2, R1 and R2. Charge will flow from 1 to 2 until the potential of both the conductors will become same. Will become equal. This is the nature. This is the nature. Means you can say, if you have a water at a greater height, always the water will flow from higher height to the lower height naturally. Like you can say electric field is from higher potential to lower potential direction. So, oh, by the way, the potential, and they are saying that after connecting with wire, this have a charge q1. This have a charge q1. I am supposing a positive charge. You can suppose any charge if nothing is given here. And we know that the charge will be on the surface of the conductor. This is q1. This is q2. Charge will be on the surface of the conductor. Inside the conductor there is no charge. When you will give the charge will appear on the conductor. So charge is on the surface, and that is why we always take the surface charge density for the conductor. So finally they are saying sphere 1 have charge q2, sphere 2 have charge, sphere 1 has charge q1 and sphere 2 have charge q2, and we have to find the ratio of the surface charge densities. Okay, fine, very good. So first thing is, both the spheres have the equal potential, V1 equal to V2, and formula for potential on the surface or inside will be same. See here, I am telling multiple concepts from this question. The potential on the surface as well as inside of the conductor is same, and the formula is K Q1 divided by R1, and this is equal to K Q2 divided by R2, and K, this is cancel out. Then you can calculate the value of Q1 by Q2 is equal to R1 by R2. R1 by R2. So consider this as equation 1. And now surface charge density sigma 1. Surface charge density is charge on the surface is Q1, and area on which this charge is distributed. Surface area of the sphere is 4 pi R1 square sigma 2 Q2 4 pi R2 square, and they are asking sigma 1 by sigma 2. So Q1 divided by 4 pi R1 square, you can write this 4 pi R2 square divided by Q2. Now 4 pi is gone. We have Q1 by Q2 multiply by R2 square divided by R1 square. Now put the value of Q1 by Q2, and they are asking here, find the ratio of their charge densities in terms of radii. We have to find the answer in terms of radius. So Q1 by Q2 is given as R1 by R2. So right here, instead of this, R1 by R2, and this is, I can write it R2 into R2, R1 into R1. So R1 is cancel out, R2 is cancel out, and we will have the answer. The surface charge density ratio of the surface charge density is R2 divided by R1. R2 divided by R. I can solve this question in half of the minute also. But I have told you the concept. You can get this question. Okay. So guys, please note it down. This is a very good question, I will say, for the examination purpose. So remember this point. Charge will always appear on the surface of the conductor. Always. When you will give charge to the conductor, the charge will appear on the surface due to the induction. Okay. Have you written this?
Yes, sir.
Matthew written?
Yeah, sir.
Nawal?
Yes, sir.
Okay. Completely written now?
Yes, sir.
Very good. So now we are back on our topic. We have just completed this. For the conductor, on increasing the temperature, resistance will increase. For alloys, the resistance will increase, but not as in case of conductor. For semiconductor and insulator, the resistance will decrease. For the superconductors, there is no resistance, and we have just did this. And now we will discuss the circuit analysis, series and parallel combination, and after that, so in circuit analysis, we have series and parallel combination of resistors, series and parallel combination of resistors, like we have series and parallel combination of capacitors earlier. Secondly, we have series and parallel combination of cells. We will discuss. Thirdly, we will discuss the series and parallel combination of bulbs. Fourthly, we will discuss the Kirchhoff's laws for circuit. These things we are going to discuss, and before that I want to tell you division of current and voltage in the circuit, in the wire, how the voltage and the current will divide, how you will take the current same, how when you will take the current. Okay, so we will discuss this division. Without this we cannot solve the circuit. Division of current and voltage, and voltage is also known as potential difference. So firstly, division of current. Division of current. Remember one point. Remember one point. I have already told you uh, in the previous classes of the capacitors. Also, we have capacitors there. Current will only divided due to the branching. Due to the branching. If you will change the wire, means you will branch the wire, the current will change. See here, this is the wire here. This is the wire, and the current is flowing in this wire right now. The current is flowing in this wire right now. If the wire is same, the current will same. Either I will do the wire like this, bend the wire, I can do. And if you, I will connect one more wire, like I have connected this one more wire like this. This is one wire and this one wire. This time from here, the current, some current will go in this wire and some current will go in this wire. So if you have a wire like this, so conducting wire, you have a conducting wire, then and resistance are connected. Resistance means the hindrance, and this is looking like if you are walking on this, so this is the hindrance. So this is the hindrance for the current. So this is looking like the hindrance also. So if the wire is same, means if there is no branching, then current is same. I represents the current. Current is same. If I have just bent this wire so many times, then also the current will remain same. Here the current will I, here the current will I, here the current will I, here the current will I. In this resistor, across this resistor, means across all the resistors, the current is same. Now, if you have the connection like this is one wire, and on this wire a resistance is connected, and from this you have taken the connection of another wire and connected the resistor. Suppose this here a resistance is connected. So see what will happen if the current I is flowing here. The wire is same, the current is I here. But from this point, there is the branching of wire. So now the current will not I here. The current will be something different. I am supposing this as I1, and here I am supposing the current I2. In this wire the current is different. In this wire the current is different. And we have discussed that we will treat current as a scalar quantity. That is why I was telling you. So now from here I can write I is equal to I1 plus I2. That's why at that time I was saying. So this is the division of current, how the current will divide. I have just given the little idea about this. Now we will see the division of voltage, how the voltage will divide. So voltage is, you can say, the you can uh, treat voltage as the energy, means work done for carrying a charge from infinity to a point is the potential, and the difference of potential is voltage, and you can relate this with the power or energy. So voltage divides due to offered by resistor. And in the previous chapter we have discussed the capacitor also. Means what will happen if you have a wire like this, then the potential of this point, means the voltage of this point, this point, potential, not the voltage. So if this is point A, this is B, this is C, this is D, this is E, this is F, then at all the point, as there is no resistor or capacitor, means no discontinuity in the path of this wire, so at all the points the potential is same. Potential is same at all points. So you can write P. And one thing I want to tell you, if there are 2 points in the wire, suppose this is one point, this is another point, this is C and this is D. At point C, VC is the potential, and at point D, you will take VD is the potential, and potential difference between C and D will be VC minus VD will be the potential difference, or you can also write VD minus VC. But I will recommend you to subtract, write first the quantity having large magnitude and subtract from that smaller magnitude. VC minus VD is the potential difference between points C and D, or this is also known as voltage. Now if you have a wire like this, kind of wire you have, conducting wire, here, 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 A, B, C, D at point E, F, G, H, I. At all the points, the potential is same. So you can say potential is same at every point. So you can say VA is equal to VV, and you can write accordingly. If I am having a wire like this, this is point A, this is point B, and this is point C, and this is point D. Now, when you are moving from here to here, this is the resistance, and at point A, the potential is A, and this resistance will take some energy. This resistance will take some energy, will spend some energy in the form of heat. So here also the potential is A, but when you will cross this at point B, there is another potential VB, and when you will cross this, you will have a potential VC, and BC, here is potential VD. So VA this time is not equal to VB, and VB is not equal to VC, but VC is equal to VD, because there is no resistance and capacitance is in between the point C and D. So if you want to find the potential difference between, if this is resistor 1, this is resistor 2, so V1 is the potential difference VA minus VV. So you will represent this potential difference between point A and B. And similarly for resistance 2, for the resistance 2, you will write VV minus VC. VV minus VC. This is the potential difference between B and C. And if you want to calculate the potential difference between C and D, this will become 0, because VC is equal to VD. This will become 0. If the connection is like this, if the connection is like this, and here is some wire, and this wire is connected with some battery, or you can say any other thing, for any power source. This is point A and this is point B. Now see, at this point the potential is VA and there is no hindrance, means here also the potential is VA, no hindrance, here is potential VA. Now moving in this side, potential is VA, no hindrance, means no resistance, VA. Very good. If now you are moving from here to here. Here the potential is VV. Here also the potential is VV. Here is the potential VV. Here also is the potential VV. But when you will cross this, if this is point C, then this will be VC. And if this point D, then this will be VD. So if this is resistance 1, 2, 3, 4. So V1, if you want to calculate, then you will write VA minus VC, potential difference between across resistance 1, VA minus VC. You want to write V2. This time V2 is not the potential, V2 is the potential difference between point C and B. I am just coming, give me one. Okay guys, so for if you want to find the potential difference across the resistance 2, you will write VC minus VB, and for the resistance 3 you will write VA minus VD. For the resistance 4 you will write VD minus VB. So in this way you can check. And one thing more I want to tell you, if I am talking about the current in this circuit, so the current, if the current I is there, so this is the branching this time. So here the current will not be I. Suppose this is current I1, and in this direction the current I1 is going, and along whole the wire the current is I1 here. Here the current is I1, here the current is I1, here also the current is I1, here also the current is I1. Wire is same, current is same. Here the current is I2. Oh sorry, yeah. This is I1 here, and this current will be I2. And here the current is I1. Here the current is so here current is I2. Here also the current is I2. Here also the current is I2. Here the current is also I2, and here is current I1. And accordingly, they will meet at this point and become the current I. The diagram is looking a little bit complex. Okay, okay, guys, you can now note it down. You can write this.
Sir, can you scroll to the last diagram?
All of you written? So
Yeah,
Matthew,
sir.
this one also written.
Yes, sir.
Matthew, you have written this.
Yeah.
Yes, sir.
Okay. Okay, very good. So, okay. This diagram is little bit bulky, but you can make it on your copy. And this thing now, I am just drawing this thing. This thing is, I am just representing this, the resistance in the. This is very interesting concept. And now we will see, you guys already know that in series combination the current is same, in parallel combination the voltage is same. Now I will prove that why in series combination the current is same, why in parallel combination the voltage, or you can say the potential difference is same. Completed all of you?
Yes.
Yes, sir.
Okay. Now we will discuss the one thing, some basic thing I want to clear here. If this is the resistance, if I current is flowing across this resistance, then voltage across this resistance or potential difference is across this resistance is given by V is equal to IR, and power dissipated across this resistance power dissipated means when the current flows and this current will passes from this resistance, and due to the collision of electron, I have told you earlier, due to the collision of electron with ions, some power will be wasted in the form of heat. So that power dissipation is power dissipated, or you can say power dissipated, heat dissipated per unit time. I am representing this power with P, and for power P you can write heat energy, heat dissipated divided by time. Means in unit time how much heat is flowing is known as power, and the formula for the power dissipated will be current square into resistance, potential difference square divided by resistance, potential difference into current. This is the formulas for the power dissipated across a resistor, across a resistor. So note it down first.
Yes, sir.
You guys are writing very fast. It means that you can complete the 3 hours paper in half an hour.
So where I'm not done. Can you scroll up?
Okay. Nafisa, you can solve the question for paper in 15 minutes. Means you
That is if I know something.
yeah, of course you will know. You can write, and in writing you can take your time. There is one more student. uh, I don't know the name. He writes, and I think she writes faster than me. I don't know how it is possible.
Done, sir.
Speed of light is 3 into 10 to the power 8 meter per second. and they are writing with that. So now we will have series combination of resistance. Series combination. Series combination of resistance. If the resistance are connected like mm, if you connect the resistance like this, if you have a wire, this is the resistance, and in this wire connect this resistance, in this wire connect this resistance, in this wire connect this resistance. So this is the series combination. Means you have one resistance, this, and connect the wire here now, and connect another resistance. Now connect the wire here now, connect another resistance. And I have told you, you can see from here to here, and this is positive, this is battery or cell, this is battery or cell having the V potential difference, or you can say voltage, the voltage of this battery that is connected to the resistance R1, R2, R3. Here, four resistances are connected in series. In series, we have connected. Now see here, current will flow from positive, the direction of current is from positive terminal to the negative terminal. So current will flow like this. Here also the current is I. Here also the current is I. Here also the current is I. Why the current is not changing? Because there is no branching of the wire. If I connect a wire from here, then the current will change. Otherwise, the current will remain same. This is the current, and what will happen? It will flow like this and this in the series combination. But if you will talk about the potential difference across R1, across R2, across R3, across R4, so suppose you have started this from here, this terminal have, if you are considering this as point A, this as point A, so this have the potential VA. Potential VA. Wire is not changing, means, oh, sorry, not the wire. There is no resistance in the path. Here is also VA. No resistance in the path. Here is also VA. But when you will cross this resistance, this VA will decrease, means this resistance will take some potential, means some energy, some potential will drop here. And at this point, when you will at this point, suppose this is a point V, you will have the potential difference VV. And when you will cross this, again the potential will drop. Suppose this is VC. When you will at the point, this point, then again the potential will drop. And finally you are at this point, E. And here again the potential is VE. Here again the potential is V. as there is no resistance in the path. So you can see here current across all the resistances is same, but now calculate the potential difference across R1. That is V1. Potential difference across R1 is, I am representing this as V1. V1. See, the value of V1 is VA minus VB. Potential at A across R1 means VA minus VB. Means across the resistance 1, the potential is VA minus VB. Across the resistance 2, VB minus VC. Across the resistance 3, VC minus VD. Across the resistance 4, VD minus VE. So you can see here all the resistances have the different potential difference or voltage. When you will talk about the current, resistance across R1 is I, resistance across R2 is I. But the potential is here different. Means the voltage is different. So see here now. This battery have the potential difference V, and this potential difference is divided now. This potential is divided across R1, R2, R3, R4. So I can write V is equal to V potential difference across R1, V2, V3, V4. I can write now. Here is V1 across R1, potential difference or voltage is V1, V2, V3, V4. So I can write this, and if I will replace this all the resistances with a single resistance, now if I replace all the resistances with a single resistance, and that single resistance is equivalent to all the resistance before, this is suppose R equivalent, and this battery is same, so current is this and I current is flowing here. So from here you can write V is equal to IR, potential difference across R equivalent is equal to V. For V you can write I into R equivalent. This is equation 2. So now put the value of V here. When you will put the value of V, of V is equal to I into R equivalent. And what is V1? V1 is equal to I, current is same, I into R1. I into R1 is V1. V is equal to IR. So you can write V1 is equal to I1, R1. This will become I2, R2, I3, R3, I4, R4. But we know that I1 is equal to I2 is equal to I3 is equal to I4 is equal to I. So I into R equivalent can be written as I. You will take I common from here. So you will have R1 plus R2 plus R3 plus R4, and I will get cancel out. Then you will have the equivalent resistance is the addition. This we know already. I have just done this derivation to show you how the voltage and current will divide. Please note it down. So that is why in series combination the current is same, because the wire remains same. There are no branching. When completed, please inform me. Matthew done?
Yes, sir.
Sir, can you scroll down?
Yeah, of course I will. Make this diagram properly.
Okay, sir.
Yeah. Otherwise, after 1 month, you know what happened. Okay, I have just replaced all the resistances with some equivalent resistance. In 10th class also we have discussed this. Means I have not discussed, your teacher has discussed with you this.
Yes, sir, finish.
Yeah. This is very easy topic. Completed, Matthew?
No, sir.
Hmm, hmm.
Done, sir.
Okay, very good. So there are some basic things we will discuss here in this. Basic, you already know these things, but I am just writing. So first thing, if you have to consider this circuit, I am talking about this circuit, okay? We have this circuit earlier, and so if in this circuit, we can find first, if we want to find the total voltage, everyone knows total voltage is V. If we want to find the total current, if we want to find the total current, that is I, total current is equal to total voltage divided by equivalent resistance. If you want to find current through each resistor, current through each resistor. So for the current through each resistor means current through resistor R1 is equal to I1, that is equal to I2. All the currents are equal and that is equal to total current. Because this is series combination. If you want to find the voltage across each resistor, voltage across each resistor means voltage across V1 is equal to I1 into R1. We know that I1 is I, R1 is this. So V1 is equal to I R1. Similarly, you can find V2 is equal to, current is same, V3, you can find I R3, and as there are 4 resistors, I into R4. If there are n number of resistors, R5, R6, R7, R8, accordingly all the things will remain same. Now I have told you power dissipation. Power dissipation, I have told you, when the current will flow and current will pass from this resistor, there will be some heat loss. There will be some heat loss in the form. So that is known as the power dissipated across each resistance or resistor. P1 is the power dissipated across resistance 1, that is I square R 1. For P2 you will write I is current is same. For P3 you will write R3. And if you want to find the total power dissipation, then simply you can add this. Total power dissipated in the circuit. Total power dissipated in the circuit. Circuit means resistance are connected with battery, is known as circuit, and along with wire. So total power I am representing with PT, P suffix T, that is equal to P1 plus P2 plus P3, and total power you can write I square R1, I square R2, I square R3. Now take I square common, you will have R1 plus R2 plus R3. And what is R1 plus R2 plus R3 is equivalent resistance. So you can write I square R equivalent. So this is the total power dissipated in the circuit. Note it down. After that, we will solve one numerical. Completed, Matthew?
Oh, wait, sir. Last time.
Okay. Nawal?
Yes.
Nafisa? You have to
Yes,
complete it. I know.
Done, sir.
Okay, very good. So now we will solve one numerical, and after that all the concepts will be clear. This is the third. This is the theoretical part, and now we will solve one numerical. And so the question is very simple question, very basic question, very. You have two resistance like this, and these resistances are connected with a battery of 100 volt battery, and this resistance is R1, this is R2, and this is given as 5 ohm. Unit of resistance is ohm, and ohm is represented like this, and this is as 10 ohm. And we have to find number one, very simple. First, equivalent resistance of the circuit. Second, we have to find total current in the circuit. Thirdly, we will find current through each resistor, current through each resistor. Fourth, voltage across each resistor. Fifth, total voltage in the circuit. Sixth, power dissipated across each resistor. Seventh, total power dissipated in the circuit. So this you have to find. You can also find these things, but I am just solving this. Equivalent resistance. R equivalent resistance is R equivalent is equal to R1 plus R2 in series. This is the series combination. See, this is a series combination. Current will be same here also. Across R1 and R2 the current will same, but the potential will here V1, here the potential not voltage is V2. So when you will calculate R equivalent, 5 plus 10, this will be 15 ohm. Secondly, we have to find the total current. Total current I am representing with I. This I am representing with R equivalent. So what is I? I is equal to total voltage divided by equivalent resistance. Total voltage is 100 divided by equivalent resistance is 15. This will be 20 by 3 ampere, the current. total current. And third, we have to find current through each resistor. We know that all the currents are same. That is equal to total current. Fourth, voltage across each resistor means V1, voltage across resistor 1, I1 into R1. I1 is equal to 20 by 3 means I value of R1 is 5. This will become 100 by 3 ohm. Oh, sorry, 100 by 3 volts. V2 is I2 R2. What is the value of I2? I2 is equal to I, and I is equal to 20 by 3 into 10. This will become 200 divided by 3 volts. Total voltage, either you can calculate total voltage from here, or you already know the total voltage. Total voltage is this 100. Total voltage is equal to, either you can add all the voltage 100 by 3 plus 200 by 3. This will become 300 by 3. This will become 100 volt. Or you can see the total voltage from here. Power dissipated across each resistor means power dissipated across resistor 1 is equal to I1 square into R1. Value of I1 square. I1 square means 20 by 3 square. R1 is 5. This will become 400 by 9 into 5. This will become 2000 divided by 9. Unit of power, SI unit of power is watt or joule per second. If you want to find power dissipated in the resistance 2, then you will write I2 square into R2. This will become 20 by 3 square, current is same, into 10. This will become 400 by 9 into 10. This will become 4000 divided by 9 watt. If you want to calculate the total power, you can either calculate with this P1 divided by 9 plus P2 divided by 9. This will become 6000 divided by 9, and this is in watt. Or either you can calculate this power, total power, I square into R equivalent. I square is, what is I square? See here, I square 20 by 3. Series combination, current is same. R equivalent is 15. So you will get the same answer. 400 by 9 into 15 for the 6 means 6000 divided by 9 watt. Are you getting or not? I am just solving. Matthew, Nawal and
Yes, sir.
Nafisa. But this is very easy question. Note it down. We have to solve little bit complex question also. Written the question already?
Yes, sir.
Yes, sir.
Matthew?
Done, sir.
Okay. So write the solution now. Now after this we will see the parallel combination of resistances, and there we will see why in parallel combination the potential difference or the voltage across each resistance is same. We know that the potential difference or the voltage across each resistance is same, but we will see why. the unit of the SI unit of power is watt or joule per second. See here, the power is energy dissipated or energy divided by time. The unit of energy is joule and unit of SI unit of time is second. Joule per second is known as watt. Like coulomb per second is known as ampere, joule per second is known as watt. This unit is named in the name of scientist James Watt. James Watt made the steam engine. So so in series combination, the current across each resistance is same, but the voltage is not same across resistances. An equivalent resistance is the sum of all the resistances in series. Done, Matthew?
Yes, sir.
Nawal, done?
Yes, sir.
Now we will discuss the parallel combination of the resistance. Just a second. Now we have parallel combination of resistances. So see, the parallel combination is like this. if you connect the resistances like this, end to end connection, end of this connected with this, these kinds of this connection is the parallel connection. So we have this connection, and I have connected a battery here, and the voltage of that battery is V. Now you can see here, if suppose I current is flowing, there is no branching, so the current is here, I current will be here. Actually, it is better to make this diagram like this, then it is easy to understand. Otherwise, this will become very complicated for you. Like this. Now it's okay. I have connected this. This combination is known as the parallel combination. Parallel combination, and here a battery of potential difference or voltage V is connected. Now see here, current will flow from positive, this is the positive terminal, this is the negative terminal of the battery. Current will flow like this, like this. See, here also the current is I, but from this point, the current will be divided. If this is resistance R1, R2 and R3, so this current I will be divided I1, and in this wire the current will be I2, and in this wire the current will be I3, and the wire is same, here also the current will be I1, here also the current will be I1, here also the current will be I2, here the current is I3. This is the current in the circuit. Now we will see the voltage. Okay. This is R1, this is R2, this is R3, and all these resistances are connected in parallel. So at this point, if I am supposing this point as A, if I am supposing this point as A, here is the potential is VA, here also the potential is VA, as there is no resistance in the path. VA, here is also the potential is VA. Now moving like this, no resistance in the path. Now you should move on the wire and see if the resistor in the path, here also VA. Okay, move like this, here also the potential is VA. Moving from here to here to here, here also the potential is VA, here also the potential is VA, and here is another point V. There is a battery, negative terminal of the battery. Here the potential will be some different. VB, move like this, VB. At this point, when you are moving like here to all at all the point, the potential will VB. Here also VB, VB, V suffix V. So now potential difference across R1 equal to, I am representing this as V1, and this V1 is given is, what is this V1? VA minus VB. Here also this potential is VB, VA minus VB. Accordingly, potential difference across R2, potential difference across R2, that is V2. This is also VA minus VB. See here, R2 VA minus VB. V3 is also VA minus VB. So see here, the potential difference or the voltage across each resistance is same. That is why we say in parallel combination, the potential difference across each resistance is same. But see here, the current is different across each resistor. Okay, fine. So as this current is dividing in three parts, so I can write I is equal to I1 plus I2 plus I3. This is equation 1. This current is dividing, so I can write I am replacing all the resistances that are connected in parallel as with the equivalent resistance. Means the equivalent of all these three resistances is R equivalent. Now I have connected a single resistance and current I will flow, and this is the potential difference of the battery. So from here you can write V is equal to I into R equivalent. So from here you can write I V upon R equivalent. This is equation second. Now put the value of I here. Okay, no problem. We have this equation. We have this equation. So I can put the value of I is equal to V divided by, and see one thing more. This V is also equal to VA minus VB. Means the voltage of battery is also equal to this is equal to V again. See the potential difference across this also VA minus VB. So for I1 you can write, you can write V1 by R1, V2 by R2, V3 by R3, and if you have n number of resistances, then you can write like this. V by R equivalent. And what is the value of V1, V2 and V3? See here, V1 is V, V2 is V, V3 is V. So V1 is V by R1, V2 is V by R2, V3 is V by R3. Now V is cancelled out from all the sides. 1 upon R1 plus 1 upon R2 plus 1 upon R3, you will get the equivalent resistance in the parallel combination. Equivalent resistance. Please note it down. So see, that is why the potential difference is same in the parallel combination across each resistor, and that potential difference is equal to the potential difference of voltage of the battery. Please note it down, all of you. And if you have any doubt, then you can ask me. And make the circuits properly, make the diagrams properly. One thing more, in capacitors, there is something different. In capacitor, in series, we have 1 upon C equivalent, 1 upon C1 plus 1 upon C2 plus 1 upon C3, like this. Series. In parallel, we have C equivalent is equal to C1 plus C2, like this. But here is different. You should remember this also. Because in capacitor, we will talk about the charge, not the current. Here V is the voltage of the battery. This V is the voltage of battery, or potential difference, you can say, across the ends of the terminals of the battery. I have just replaced these resistances with R equivalent. This R equivalent is equal to the sub, or you can the resultant of these three resistances. Matthew, completed?
Yeah, sir, you can scroll down.
So, Matthew, you can ask me now when completed.
Yes, sir. A bit more up here then.
Yeah, because this In the next class, we will solve one numerical and we will continue with some new topic. Done? All of you?
1 second, sir. 1 second. Done, sir.
Okay, guys. Now you can leave, and we have started from here.